In the year 2062, there's a robot housekeeper named Rosie who does all the housework for an animated family called the Jetsons. Remember them? Home robots of our own time, like Roomba, aren't Rosie. But one of the exciting advances in robotics has been to realize this dream of bringing robots into our home. And those robots are useful, safe, reliable, easy to use, and affordable. These 5 features make it possible for robots to transform work in our homes, just as surely as robots transform work in factories. But could we have a more flexible home robot? Even though Baxter is designed for flexible and repetitive work in the factory, we could bring it home and find ways for it to help out. Now, Baxter's not built to work at home, but Baxter is trainable. And so what I want to show you is how we might train it if we were to have it at home. And training is really easy for Baxter. It's set up not to be programmed, but simply to be touched. So I touched Baxter's training wrist here. Baxter looks on over, shows me that I've got its attention. And then all I have to do is move Baxter's arm, and it will memorize those motions. So that's what makes this such a flexible robot in the factory setting. Now, in factories, what we would do is we'd have very repetitive things happening like a conveyor belt. We'd have objects that were always in the same spot. And so at home, that would never happen, right? If we were to put things like cups after dinner in an arrangement, we might as well clean them and take them into the kitchen. So let's do this thing that is even more flexible for Baxter, which is to let it use its sensors. And here's what's really cool. Baxter actually has sensors in its wrist. Here's a camera, and here's an IR rangefinder right there. So we can ask Baxter to be less precise and more flexible. So in the language of factory robotics, where you would do a blind pick and place, you would always know an object was where you were going to pick it up. We're moving from that into a flexible sensor-based kind of process. All right, so I've already trained Baxter to look for cups, pick them up, and stack them. Let's see how it does. So it's using that camera, and it's looking for orange objects. And it's found right away one of the cups here. It's going to pick up the cup, take it over, let's say, to the kitchen sink here, and place it in the kitchen sink. My family is very happy, right? Picking up the table is not one of the favorite things that we have to do in our household. It's found another cup, it's gone over here. So it takes a little bit more time than a blind pick and place. But again, we haven't had to structure the world in order for Baxter to do this. So Baxter is going to now look on the table for this other orange object. Let's see if it can find it. Oh, it's got that other cup. Now I've played a little bit of a trick on Baxter here to show you how this is working. This final cup that needs to be picked up is actually outside of Baxter's search area. So one of the great things about robots is they don't get frustrated with you when you play tricks on them like this. So Baxter's not going to start groaning or anything like that. We'll let Baxter look. It's not finding it because it's outside the search area. I'm just going to bring the cup right back over, and now it'll be nice. There you go, Baxter. And Baxter locates it right away, picks it up, takes it over with the other ones, and what do we have here? We have a job well done. Thank you, Baxter. Moving Baxter from the factory floor to our kitchen counter takes us into the broad realm of service robotics. The International Organization of Standardization, ISO, offers this definition: a service robot performs useful tasks for humans or equipment excluding industrial automation applications. So if Baxter serves food or coffee, he becomes a service robot. Service robots can be of 2 types, professional or personal. So if we bring Baxter, the industrial robot, to work in our home in a way that pretty much anyone could use, we would now call him a personal service robot. If we took Baxter off the manufacturing line and had it work in a hospital, a store, or a public park, where a trained operator is probably on hand, we'd call that version of Baxter a professional service robot. Now, these distinctions matter because they recognize that a robot is the job that it does and what it's designed to do. Now, flexible robots like Baxter really are the exception. Most of the time, different jobs are done by different robots specialized for one job. For robots designed to work at home, 3 features are proving to be the keys to success of personal service robots. They're specialized for one job, they're of small size, and they possess autonomous mobility. An important part of being a specialist is that the robot doesn't need to be reprogrammed. Specialists have one job to do and they do it out of the box. Now, Roombas, for example, weren't the first home robot vacuum. Electrolux had introduced a robot called Trilobite in 2001. But Roombas were the Model T of robots, the affordable and reliable machine for personal use that transforms lives. Like any successful commercial product, Roomba has attracted competitors, including Neato, Navibot, HomeBot, BobSweep, D-Bot, and traditional vacuum makers. And Roomba itself has undergone a regular series of updates and improvements that tell us a lot about what's happening in modern robotics. In 1997, iRobot was making a Roomba prototype called Dust Puppy. Dust Puppy was more like a dust mop than a vacuum cleaner. It had a white pad that was just dragged around the room. But Dust Puppy was very important as a proof of concept. It showed that you could use very simple behavior-based control algorithms to have a mobile robot navigate around your home and get a job done. By 2002, the first model of Roomba was sweeping and vacuuming. One of the really important design features is that Roomba goes where you don't see or normally go, under furniture. This immediately explains a decision that iRobot made about the design. It had to be small in height in order to fit under furniture. In 2004, iRobot introduced the second generation of Roomba, originally called Discovery, but then renamed the 400 series. Roomba 400s had advanced autonomous navigation, adding a new algorithm allowing it to measure the size of the room itself, using the longest path it could travel across the room as an estimate. To measure distance, Roomba 400 series would use a sensor to keep track of the number of revolutions of its wheels. These Roombas could also be programmed to clean on a schedule, and they had a bigger dustbin than the original models. In 2007, iRobot introduced the 500 series, which you see here in our laboratory. So this is practically an antique, but I love it. It works really well, and it shows a technology that had already come into its own. In this third generation, iRobot added automatic docking for autonomous recharging of batteries. The 500 series Roombas also moved faster and needed forward-looking IR sensors to prevent high-speed collisions. The third generation Roombas also avoided getting caught on cords by reversing the brush's rotational direction if resistance was encountered. The success of robot vacuums has led to lots of other small and specialized home robots to choose from. In 2005, iRobot introduced its second home robot, Scuba. Its job was to scrub floors, and the Model 450, introduced in 2014, used a 3-pass cleaning process that includes vacuuming as the first step. It vacuums, and then Scuba lays down a thin film of cleaning fluid to pre-soak the floor. On the second pass, it scrubs and squeegees, sucking up the dirty solution. The final pass continues to remove the liquid. Scuba provides an important lesson for the design of robots. Once you've invented the wheel, you don't have to reinvent it. The wheel, in this case, is the basic circle-shaped design for a floor cleaning robot in the home. Roomba shows us just how successful a hockey puck shape can be. A circle lacks edges to ding and get caught. The short stature, too, is great, as we've seen, for getting under furniture. So what we have in terms of a robot body is one that's built to get under and around. Scuba uses this same basic strategy in its body design. Now, we find an exception to the circular body design in iRobot's own Brava, a robot that either does dry or damp mopping. Now, why a square body? We've just been talking about how good body design reflects the function of the robot. So what gives? Is it hip to be square? Why do something different? Here we go, trade-offs. While behavior-based control architectures are simple and robust, how they clean is inefficient. Some areas get more coverage than others. Dirt Detect helps focus the robot on one spot, but then some spots may not get coverage. To make sure that most areas are covered, Roomba and Scuba are programmed to make multiple passes. That takes more time, more battery power, and that's where the inefficiencies come into play. Thus, the trade-off for behavior-based cleaning is simplicity and robustness versus efficiency. iRobot figured out, because they asked, that some people would prefer more efficiency in their cleaning robots. So to create an efficient one-pass cleaning robot, iRobot needed to create a robot that could navigate using a map. Now that's not behavior-based robotics, is it? So GPS isn't a good option inside for two reasons, and that would be what we would use outside for navigation. So the first problem with GPS inside is that the signals from satellites can be scattered, distorted, and blocked by walls and metal structures. Second, even if you can get a good GPS fix inside, the accuracy of the traditional consumer fix, even in the best outdoor conditions, has been about 3.5 meters, or just over 10 feet. That's just not sufficient accuracy to guide indoor robots. So what to do for navigation inside? Say hello to Brava. Actually, hello to Evolution Robotics, which built a navigating robot called Mint. When iRobot acquired Evolution Robotics in 2012, Mint was renamed Brava. Brava works using this totally cool thing called an infrared navigation system, which they call North Star. The North Star system uses a beacon that sits on a table and projects IR dots onto the ceiling. Brava uses 3 infrared sensors to detect its distance from those dots and then triangulate its position. iRobot talks about this as the functional equivalent of an indoor GPS system. And when iRobot patented their own version of North Star's infrared technology in 2010, they called it Celestial Navigation. Brava uses IR navigation common to North Star and Celestial Navigation to create its own map of the room. Now, here's the slick trick. Knowing its position on the map, Brava can plot a course that moves it back and forth across your floor in beautiful, tight rows. This gives complete coverage in one pass when Brava is dry mopping. In damp mopping mode, Brava still navigates, but it moves with a side-to-side and back-and-forth scrubbing motion as it moves along the rows. So creating a map and knowing where you are on the map at the same time is a hugely important task in autonomous robotic navigation. And it has a special name. It's called SLAM, which stands for Simultaneous Localization and Navigation. This is model-based controller architecture that is computationally intensive. Now, this gets us towards an understanding of the square design. If you know where you are and where other things are on your map, you can plot your course to avoid objects. And if you know what lies ahead, obstacle-wise, the square design is less likely to get you stuck in a corner. You avoid the corner, and you can also aim deliberately into the corner. Also, what Brava can do is put the cleaning pad out front like a plow, and it makes it wider than the body. So a wider cleaning pad means fewer passes, even better efficiency. Sounds great, but we should always ask the question, what's the trade-off? There are a few with Brava. First, because it has that wide mop out front, Brava doesn't head straight into a docking station like a Roomba. While you could have Brava turn and back into a charging dock, you'd need to add an IR beacon sensor and a bump sensor to the back end to make this happen via sensor-guided movements. You could do that for sure, but because the cleaning modules get dirty and they need to be removed and cleaned, you have to pick up the robot anyway. Second, in spite of having a map, Brava does sometimes get stuck in small areas where it can't maneuver itself out. Think about it this way. You can maneuver into a slot that is exactly your width. If you are round, you can rotate in the spot to help get out, but if you're square, all you can do is back out exactly straight back, or else you wedge yourself in. Third, Brava has to have a good signal from the North Star IR navigation system in order to clean your whole space. It can clean a small area without navigation, but that's not really the point, right? So where you get into trouble is if you have angled ceilings and ceiling fans that can interfere with the navigation signal, as can plasma televisions and fluorescent lighting, both of which emit infrared light. Once the cleaning cycle has started, you also have to take care not to move the North Star beacons. The navigation system has to be tuned to make the system work optimally. So the big trade-off for Brava is between efficiency and robustness. When it works optimally, Brava can navigate and clean very efficiently. But because it's dependent on map-based navigation, it's not as robust as Scuba. So really, Scuba and Brava are very complementary. They clean differently and with different trade-offs. These SLAM systems that we've talked about for indoor navigation are becoming much more popular in personal service robots. Nito, a competitor of Roomba, pioneered SLAM navigation using a completely different system. Lasers! And not on sharks, right? See the flat edge on the body? That square is groovy body plan is a big clue that Nito is using map-based navigation. LG's HomeBot, with a slightly rounded square body, is another robot vacuum with map-based navigation. Well, so what? Well, for example, the Nito or the HomeBot can go for a charge, then return to where it left off to finish a job. So what's the trade-off? Well, Nito's laser is somewhat delicate, and if damaged, the robot may not even find its way back to the charging station. So again, same sort of trade-off, maybe less robust, but more efficient. Now, the Dyson 360i, first introduced in 2014, combines a circular body with a mobile-based control system. That mobile-based control system is based on a model. So the 360i refers to a panoramic camera that takes a couple dozen photos every second, which are then digitally combined to create a current map of the room. The frame rate for the photos matches the speed of the moving robot, and each updated map is combined with infrared sensing of nearby objects, both to avoid nearby objects and to plot an efficient course for cleaning. The Dyson robot also boasts tank treads instead of wheels, with the treads affording better traction and better transitions over uneven surfaces between rooms or even over some objects left on the floor. Does even Dyson have a trade-off? You bet. More powerful vacuum, but too tall to fit under some kinds of furniture. Another popular type of home robot actually works outside, in your pool. Mira 530 is an autonomous pool cleaning robot built by iRobot. Mira has wheels for locomotion on the surfaces of your pool underwater, and also a rotating scrub brush. It also filters water, which it sucks in through an opening up front, so it removes both small particles and large items like leaves. Now, what I find most impressive about Mira is that it can move up vertical walls and navigate steps. Its wheels help give it traction, and the suction it creates for filtering water helps it hold its ground. Unlike Roomba, Scuba, or Brava, Mira has a tether. Now, a tethered robot usually indicates one of several things: remotely controlled, an external computer controller, and/or an outside energy source. For Mira, it's the energy. The cable is a low-voltage energy source from a topside transformer that is converting alternating current from the household energy supply to the local direct current that Mira uses. Low-voltage direct current is very safe to use around water and people. That's the trick. Now, don't try this at home, but you can take a 9-volt battery, if you wanted to, and stick it on your tongue. That's a low-voltage direct current. And you'll feel a little bit like a salty, buzzy sensation in your mouth. There's no harm done, but it gives you a sense that DC current systems are actually very safe. And they're safer, really, for two reasons. First of all, it takes 10 times as much DC current to cause a dangerous electrical shock as AC current. Mira operates at 29 volts DC with a maximum current rating of 6.3 amps. Since the electrical power is the product of voltage and current, the maximum power that is available through Mira's regulated and fuse-protected energy supply is about 180 watts. Roomba, by contrast, draws about 30 watts. A typical 12-volt car battery can easily allow a current draw of 500 amps for an electrical power production of 7,000 watts. That's much more than the power Mira is using. By the way, I would not put the context of a car battery to my tongue. Okay? And here's why. Because a large battery has much less internal resistance than a small battery, it would draw much more current, more power, and really burn my tongue and actually probably cause my heart to stop. So why not just use a battery for Mira? What's the trade-off when we use a battery? On the positive side, being untethered means you won't get tangled if you go under or through legs of a chair, or you won't have to stay in close proximity to your external energy supply. On the negative side, Batteries have a limited time for which they can supply electrical power. This is measured as amp hours. If you look carefully at batteries when you buy them, you'll see that they come with an amp hour rating. For example, a typical carbon zinc AA battery, which is rated at 1.5 volts, has an amp hour rating of 1,000 milliamp hours. Want more time to operate? Then get a bigger battery. A typical carbon zinc D battery, 1.5 volts, has a rating of 8,000 milliamp hours and would last 8 times as long as the AA battery with equivalent electrical loads. Batteries boil down to this. To extend that mission time, you can put in a larger battery, but bigger batteries increase the weight that you have to lug around. So the designers at iRobot had a choice. Give Mira a big enough battery to handle the high power needs of the 3 motors over enough time to complete 3 jobs of scrubbing, locomoting, and filtering, or power Mira through a tether with a topside energy supply. A big battery, being full of dense metals, would be great for keeping Mira on the bottom of the pool, but the problem would be climbing the walls, when the weight of that battery would tend to peel Mira off. Now, the way to counteract this would be to create much more suction. But more suction makes it harder to move. You could increase the power to the motors driving the treads, but then that's more power that you need. So you see, this is one of those vicious circles. So by giving Mira a tether for its energy supply, the designers were able to give Mira the power to climb the walls and even scrub right at the waterline, where the robot has to support part of its weight out of the water. More importantly, Mira's effective time on station was increased, with time limited now only by having to stop and clean the filters. But the tether and the cable, how to keep Mira from getting tangled up? The trick is that Mira has a gyroscopic sensor on board. Gyros measure accelerations that come from gravity and turning. So this allows Mira to keep track of how it's oriented and how many times and in what direction it has turned. Very cool. So after a number of turns in a certain direction, Mira is programmed to turn back. This removes the coils in the tether and prevents tangling. So you can use this idea in your own pool, or in your own robot, provided that it has a gyroscope that is measuring acceleration in the plane your robot is turning. When we turn, we create a spike in acceleration. You can see how this would work using a free app on your smartphone, and I encourage you to get one. That's really fun with an accelerometer. So most smartphones have a 3-axis accelerometer, and this sensor is needed to adjust the screen to how you are holding it. The key acceleration measured is that due to gravity, so the screen tends to rotate to remain upright depending on how you're holding that phone. If I had my acceleration app in my hand, if I rotated quickly, I could see a spike in the lateral direction. Now this isn't due to gravity, but instead due to the motion of that phone. And if I had that accelerometer on my robot, I could keep track of those acceleration spikes. Those indicate the turns. The direction of the turn is indicated by the sign, positive or negative. Positive is one direction and negative is the other. So if you built a robot that carried a tether, you could keep track of how often it turned and make sure that it unwound the tension it was putting on a cable. And what's really nifty about using an accelerometer this way is that it is part of a process called inertial navigation. We humans have inner ears that work like an accelerometer, so we can keep track of how we turn and how we are tilted. Many other animals have this kind of ability too. One way to simplify the sensors that you need in order to navigate is to simplify the workplace, to structure it. A great example of a highly simplified workplace is a linear stretch of gutter. The gutter is a great example of a structured workplace. Gutters vary a little in shape and width, but the overall job is predictable. What is not predictable is the kind of clutter that you have in your gutter. But if your job is to get stuff out of the gutter, that's a common function across all types of debris. Now, a robot that does this job is Luge, the gutter cleaning robot from iRobot. It spins an auger and then uses tank track actuators to push that actuator along. An auger is a type of end effector for drilling. But here, with Luge, the idea is to take the same rotary action and use it to move material to the sides rather than to the rear. A much less structured outdoor workplace than the gutter is the lawn. We've got stable but irregular obstacles like plants and sheds. We have terrain of different types with rocks, hills, steps, pools, and ponds. Yet lawn mowing is a job proven to be well suited to robots. In fact, after robotic vacuum cleaners, robotic mowers are the second largest group of home robots in use. The first robotic lawnmower was Mowbot, and the technology for it was invented and patented by S. Lawrence Bellinger in 1972. His patent, assigned to the short-lived company Mowbot, included the basic design that is still used today by robotic mowers. The key to the navigation system is a boundary wire. This is essentially an invisible electric fence buried shallowly in the ground. So if you have an invisible fence for your dog, it's the same idea. The wire is plugged into alternating current and generates an electrical field that can be sensed by the robot using magnetic coils mounted in the front and the back. In response to the sensing the field, the robot turns and heads off in another direction, kind of like what we saw with the cliff detectors here with Roomba. And it looks very much like that kind of escape behavior. And just like Roomba, Mowbot covers its workplace, the lawn, in a random fashion. Given enough time, most of the floor, or lawn in this case, is traversed and cut. The efficient row-by-row systematic approach has only been tried more recently. In 2012, Bosch introduced a map-based mowing robot called Indigo that mows in parallel lines. But Husqvarna, maker of the automower robots for the lawn, hails the random cutting pattern it uses for two reasons. First, that random cutting pattern doesn't produce lines in the lawn, and two, it helps reduce the growth of moss. Who knew on that second part, eh? But Automower uses the boundary wire to define the perimeter of the lawn and to define areas that are off limits, like your flower garden. So this boundary wire is the functional equivalent of physical and digital walls for an indoors robotic vacuum. A second type of buried wire, a guide wire, can actually be used to help lead the mowing robot back to its charging station or through tricky terrain. Husqvarna's Automower Model 260 ACX comes with a wireless communication module that allows you to communicate with it and use GPS to track its general location. The GPS is not precise enough for the robot to navigate itself, and the robot will text you, though, if it runs into trouble. Kind of nice. A big issue with autonomous robotic lawnmowers is safety. To prevent or reduce the probability of accidental cutting, the Automower has a lift and tilt sensor so that it stops rotating the cutting blades the moment that it is picked up or begins to tip on over a slope. We saw that same kind of thing in Roomba. A bump sensor up front gets the mower in reverse upon contact with a tree. And the Automower uses a battery to power its electric motor. This keeps it running more quietly, roughly 60 to 70 decibels compared to 90 to 100 decibels for an internal combustion mower. Like Roomba, the lawnmower from Husqvarna has a recharging dock to which it can return autonomously. Because it doesn't rely on visual sensors for navigation, believe it or not, it can also mow in the dark. So the trick is that you can schedule it to be mowing more than just once a week. Let's look at one more household job that robots can do for us: clean the windows. WinBot, introduced in 2011, can do the job. WinBot is created by a company called Ecovacs, a Chinese company that has commercial operations in Europe and North America. WinBot has an actuator system that creates suction that keeps it on the glass. It has IR proximity sensors that allow it to calculate the size of your window, and then, like Roomba, it calculates a plan to clean that whole area. Now remember, an IR sensor is an active sensor. It sends out a signal, a beam of IR light that we can't see, and then it records the intensity of the reflection off the frame of the window. Now in terms of a workplace, a window is very structured, very predictable, with no obstructions. So the task is straightforward. Drag a cleaning pad over that window. But what makes this workplace and the task challenging, of course, is that it's vertical. So Ecovacs had to focus on locomotion. WinBot uses two suction rings to hang on. But the suction can't be too tight, just like we were talking about with cleaning the pool, or else it couldn't be able to move. So again, there's a balance between supporting the weight of the robot and allowing it to slide around the window, so it's powered by two tracks that are on the side. Now, as we saw with Mira in the pool, moving vertically places a premium on being lightweight. WinBot takes the same approach. No battery. Unlike Mira though, WinBot doesn't worry about tangling the external power cord, so no gyroscope is used. For mobile home robots, such as cleaning robots, the purpose of their movements is typically to provide what we call coverage. You want your robot's cleaning to cover the entire area of the floor, the pool, the lawn, or the window. But not all home robots are built with coverage in mind. Atmobot, built by Ecovacs starting in 2010, moves using an algorithm that we call gradient climbing. Atmobot has sensors that can detect smoke and other airborne pollutants, and as it moves, Atmobot can detect the direction in which the smoke is coming by comparing the difference between the signals in two different sensors. The simple control algorithm is that you turn in the direction of the sensor that has the strongest signal. And if your sensors have the same readings, the simple control algorithm is to go forward. Once you've found that straightforward direction, the robot is moving up, or climbing, we call it, the gradient. Now, a gradient is anything for which there is a difference. We can talk about a temperature gradient when we jump into a lake. The surface waters are warm, but we dive and the water gets colder. Inside the home, the concentration gradient for cigarette smoke goes from a low concentration in another room to a high concentration right at the source of the smoke. Following gradients and covering ground have very different implications for navigation, but gradient following and coverage are complementary and are used sometimes in the same robot. For example, Roomba begins its cleaning with a spiral, and this is a coverage move. And if Roomba detects an area with a lot of dirt, it begins a focused coverage behavior called spot cleaning. But when Roomba is using its IR beacons to navigate to the charging station, it's engaged in gradient climbing, using the IR signal from the beacon to head directly towards it. Effective and successful home robots thus far have been small, mobile systems that specialize in one job. But as larger robots appear that can move safely with us in our homes and other spaces, size alone will open up new kinds of jobs for them. A taller robot can reach countertops, load and unload high cabinets even, dust a ceiling fan, and so on. A legged robot can negotiate stairs and help ferry materials into and out of storage. I mean, I would love to have a robot that can take my dog outside and even do some of my dog's jobs like patrolling the garden for furry intruders and keeping squirrels up in the trees. As home robots and other service robots gain more skills, and perhaps even a humanoid form, they, like Baxter, will move from narrow specialists towards becoming broader generalists. We'll increasingly be able to train our robots easily and quickly to do new tasks that are unique to our needs and spaces.